Max Gosselin. I am a chemistry major at McDaniel College. Today, I'm going to be sharing with you my summer research on the coronavirus. First, let me begin with some background information on the virus. The virus was first discovered in 2002, and it was linked to an outbreak of a severe acute respiratory syndrome known as SARS. In 2019, another outbreak of SARS occurred in Wuhan, China, and this virus went to go spread on and cause a pandemic. So pharmaceutical companies have raced to decide to create a therapeutic antiviral to inhibit the viral replication cycle. To inhibit the viral replication cycle, scientists are targeting two proteases, one main protease and the other peptide-like protease. Both of these proteases are cysteine proteases, which are responsible for cleaving the coronavirus polyprotein into its active components. As you see in the figure, there's a red box around the PL-Pro and M-Pro. The original strategy was to target the main protease. Our design of our molecule was to use two different things, peptide-based capsid inhibitors and naphthoquinone-based compounds as fragments. So as you can see, there's a top figure, which is in red, shows a peptide with the polyleucine and an aldehyde as our warhead. And the bottom structure shows a naphthoquinone. We took these structures and combined them. So the synthesis of our amino acid-based naphthoquinones. As you can see, there's two different syntheses in the top and bottom. Both start out using a Michael addition. And then, as you can see in the top, there's an additional step. In the additional step, we perform the hydrolysis to cleave off the methyl, ethyl, or 2-butyl group and get into a carboxylic acid. The synthesis of our aldehyde-based naphthoquinone occurred in two steps. The first step was a Michael addition. The second step was known as the Des-Martin oxidation reaction. So based off our results, we found various different inhibition rates of the peptide-like protease and the M protease. As you can see on the structure on to the left, MCD359, we had a 15% inhibition of PL-Pro and 2% inhibition of M-Pro. And on the right, MCD360, 17% inhibition of PL-Pro and 0% inhibition of M-Pro. The structure-activity relationships of leucine derivatives was some of our more pivotal compounds in this study. The figure on the top left, MCD397, had a 21% inhibition of the peptide-like protease and 7% inhibition of the main protease. MCD363, that one had 57% of the peptide-like protease and 63% inhibition of the main protease. And the figure at the bottom, MCD362, that one had a 66 inhibition of peptide-like protease. The structure-activity relationship for proline and valine derivatives. On the figure on the top left, MCD406, had a 34% inhibition of the peptide-like protease, but 0% inhibition of the main protease. MCD407, the figure on the top right, had a 51% inhibition of the peptide-like protease and 3% inhibition of the main protease. The figure on the bottom left, MCD415, had a 2% inhibition of the peptide-like protease, but no inhibition of the main protease. The figure at the bottom right had a 19% inhibition of the peptide-like protease and 8% inhibition of the main protease. The structure-activity relationship of our aldehyde-based derivative, MCD416, had an 83% inhibition of the peptide-like protease and 20% inhibition of the main protease. When we first began the study, we saw that a long amino acid chain would increase the main protease inhibition. Based on the data, having a chloronaphthoquinone helps to inhibit both the peptide-like protease and M protease. We also discovered that carboxylic acids are more potent than esters. Also, leucine is the optimal amino acid of those tested. We also proposed that our aldehyde might be better than a carboxylic acid for our warhead. Our future work includes having amino acids related to leucine, also using leucine-based naphthoquinone with an aldehyde. Finally, creating a di- or tripeptide-based naphthoquinone. I would like to thank the McDaniel Chemistry Department, the McDaniel College Summer Research Fund, and support from the Richard Fund, the Schofield Fund, and the Don A. Fund. I would also like to give thanks to Dr. Dana Ferraris for his guidance and mentorship. And finally, I would like to thank the rest of the group, Zach, Priscilla, Jace, and Zoe, for their support.